My name is William Huang, and for my ISM topic, I've been studying machine learning for the past year because of my fascination with artificial intelligence. The field has grown so rapidly in less than a decade and has made its applications to the world known in so many ways that a world without them can no longer be conceived of in this modern technology age. For this presentation, I plan to introduce what the ISM program means to accomplish with its students, present my research into machine learning that I've been delving into for the past year, and follow up my product's development in machine learning. First off, ISM is made up of three main parts that each have their own meaning that make up the whole of ISM. The first part, independent, describes the workflow and topic selection. Because each student in ISM gets to select their own topic, the class is unlike any other. There's no real concrete curriculum. Any due dates are made by you. Aside from some progress checkpoints, other than that, how you go about tackling each problem you face is largely on you. You go at your own pace. The second part is study, which describes the research of the selected topic and the creation of a new product. You spend your year studying the topic, going through scientific papers, interviewing people, professionals, and other primary sources to gain a basis of understanding for what makes the field tick and what are its problems. You can then find a product idea that you developed to solve those issues of the field, improving it and making a lasting contribution to the field. The last part is mentorship. In the studying process, you find a professional in the field, usually outside of the school, who acts as a guide into your topic to help navigate through it and create your finished product. They are with you the whole way in its development, in your research, to guide your education. For my mentor, I contacted Owen Huang, a Duke graduate student and CEO of Gradient Health, a company working on ways to implement machine learning research into medical applications. This allows AI to have a place in something as important as the field of doctors. Because of our circumstances, the majority of routine mentor meetings we had throughout the year for ISM took place on call online. Meetings would generally consist of me asking questions I had and Owen guiding me to the right place to look, often leading me to find published scientific papers and experimenting with some code. An added bonus for the nature of these meetings is that we were not as affected by the coronavirus. But let's delve into what my topic actually is, because it's come to my attention that some people, when they see machine learning, are a little confused. So let me explain. For those of you who do not know, the term machine learning refers to a computer's ability to train on a data set and make predictions that are not explicitly coded in. It's interchangeably used with artificial intelligence. Its applications, different types of models, and optimizations of machine learning are mainly what I focus on in my research on how a machine learns to do a behavior and recognize patterns as well as a human being. I feel that machine learning has developed under the radar for most people, but any professional website or service or tech company has implemented machine learning to some degree, and these are just a few of the examples. Now, you can also try a sample of machine learning at home using these two apps. These two apps for iOS being eye detection and for Android being object detector are both object detecting models. They will give you a bounding box for objects that it's been trained on. In both of their cases, they've been trained on the COCO dataset, which stands for Common Objects. The common objects mean things like bottles or monitors or, say, tables, chairs, people, anything in your general vicinity. It will use your camera and output a bounding box, and it will show you how it's able to detect those objects, how it's able to see. And if you do more research, you can also learn how it's, well, learning. So, why do I want to get into the machine learning scene now? Well, it's because there are so many resources that are available in today's environment. Data sets and competition programs like ImageNet, Kaggle, and pretty much every other data set that is available on those websites and many more allow people wanting to go into machine learning easy access to training data, easy access to learning the steps that go into machine learning. Namely, ImageNet and Kaggle are the most important. Both of these websites encourage competitions and collect data sets for people to judge, challenge, and even win prize money. And these programs have functioned as motivations, as engines that have driven innovations in machine learning. As of 2015, because of these innovations, machine learning models have even surpassed the pattern recognition of human beings, being able to identify more accurately in object identification competitions and continues to improve year by year, even to this day. The implications of this being that computers are getting so incredibly good at pattern recognition that they could possibly find new patterns to identify objects by better and faster than any one person could reasonably do. So here is an example of what object identification or classification looks like. The computer has been given a list of options, in this case, a list of dog breeds, and is given an image input, say a dog or in one of these cases, a cat. It will then output a decision on what it believes it is seeing. Here, this is a pre-trained model off of ImageNet, and so it is already pretty good at detecting dogs. Sorry. A level above object identification is object detection, which adds localizations to its output. Recent models like YOLO v3 are so efficient that they have even allowed object identification to happen in real time, as you can see here. This is built off of part of a video that was made to showcase YOLO v3. If you look it up on YouTube, you can see the whole thing. It's just a very good video showcasing all of the applications that and capabilities that YOLO v3 has. The next level up is object segmentation, where the output includes every pixel that makes up an object, allowing the model to mask an image and define its position relative to other pixels, making for a more precise classification than bounding boxes in object identification. The most interesting use of machine learning applications is in the medical field. Here we see a utilization of object detection that's making a box around what it can be seen as either a possible lesion or abnormal growth in this lung CT scan, which leads into what I want my final product to be. I want to create an application that uses machine learning to solve a medical identification issue, identifying, in this case, pneumothorax from an X-ray scan, which is a condition that fills the chest cavity with air outside the lung and displaces the space in the lungs, shrinking them. When you look at an X-ray of someone who has pneumothorax, as you can see here, there is considerably more dead space between the chest cavity, and it can be kind of obvious for such a drastic case such as this. But some cases of pneumothorax are a lot more subtle. So I wanted to create a machine learning model specifically made to catch those more subtle pneumothorax problems. The first step into my product's development was getting familiar with TensorFlow libraries. TensorFlow libraries is a programming library which is used to code machine learning processes. And how it manages image segmentation, luckily, is well documented in TensorFlow. TensorFlow provides ample guidelines that help me create a working example model here. So here we can see the model that I've created slowly training itself in image segmentation. Because I'm trying to understand TensorFlow's image segmentation in concept, I'm able to use this toy data set basically of cats and dogs. So you can see that the model is slowly able to find the difference between what is a cat in this image and what is in the background. The next big step in my product's development was learning how to use and manipulate large data sets from Kaggle. For this step, I used a data set that used ultrasound images on nerves inside the neck as another stepping stone in the process of creating a data pipeline, because this would be my first time creating a data pipeline. So if I learned to do it in this step that was provided by Kaggle, I would be able to transfer that knowledge to a harder less organized data set like lung segmentation, which goes into the next step, which is lung segmentation. I had finally moved on to x-rays and implementing pneumothorax masks on top. You can see in the grayed out areas of some of these x-rays, there are the pneumothorax masks, which show that these are the problem areas. These are the, say, bubbles of gas or the bubbles of air that is being taken up, that is taking up lung space. And finally, the last step, 100% complete, I will show my notebook that could actually keep the code and show my model's predictions. However, as of right now, in the dress rehearsal, I do not have my product 100% complete yet. So for now, this is just a placeholder. In my product's development, there were a couple roadblocks that I ran into as I worked on the product. The first problem was the type of model to use. Over the course of my research, over the course of the scientific papers I had been guided to by my mentor, I had discovered that there are many, many models to use, many models to base your computer on. And so it can be hard to choose just one, especially since each of these models have different advantages and disadvantages and complexities that could be hard to understand with one read through. And so the way I solved this problem was just implementing multiple models onto the data set and comparing their end accuracies at the end of the training. This allowed me to objectively compare between each of the models which one is best for my specific dataset. Next problem was timing. Training for the toy dataset could take up to, say, it wouldn't take more than a minute to train through the whole dataset and get pretty decent results. However, the larger medical datasets, when trained in the same way, could take up to 10 hours if left unprocessed. This is because the larger datasets were many times larger in both quantity and resolution, as in there were many, many more images, and these images were much more high definition, had much more information in pixels. This was solved in the program by resizing the images. This way, I could sacrifice some of the resolution in exchange for a more bearable training time because I don't have all the time in the world. The last problem was memory limitation. GPU restrictions on Google Colab, which is the notebook program that I used, would often crash because of how I handled the data, which was my naivete. Because when I presented this problem to my mentor, he analyzed my code and concluded that I was utilizing the data inefficiently. So the way I solved this problem was my mentor helped me to look through some of TensorFlow's libraries to more efficiently and more cleanly restructure the data pipeline to use less memory, make my model usable and more stable. I would like to take this time to say how grateful I am to my mentor, Owen. Every step along the way, your guidance provided in my education was irreplaceable. I really could not have created this product without you, and the things that I learned in machine learning, I'll keep for me forever. Thank you so much for what you've done for me. Now, I will also be able to answer questions because this will be uploaded onto YouTube, and I will be active to answer any questions that I can. So let me know if I could elaborate on a subject outside of this presentation regarding machine learning. So, because I know for sure that I couldn't have possibly covered everything. Thank you so much for watching, and I hope you have a great day.